right. How many CIS students does it take to put up a PowerPoint? My name is Shah. This is my partner, Geoff Vasudevan. And we have a third partner, Goldman, who is unfortunately out with the flu today. Our advisor is Dr. Ives, and we are very excited to present to you the Smart Skins. It's an embedded sensor network, and the problem that we're trying to solve is that of home automation. We've taken an object-oriented approach where we are trying to represent your real-world objects, like your washer, your dryer, and your refrigerator, as programming objects, and we're trying to interact with them as such. So for example, we're trying to make statements like, if my shower turns on before 11 a.m., then turn on my coffee machine. Or if my washer turns off but my dryer does not turn on, then flicker the lights and let me know. So we're basically trying to create relationships between the legacy appliances or the appliances that already exist within your home using a programming interface and one that we're comfortable with, the object-oriented approach. And so our objectives are threefold. One is to provide a platform for a user to interact intelligently with their devices. More specifically, we use a Smart Skins device, which we'll show you in just a minute, which collects a bunch of sensor data from its vibration sensors, light sensors, temperature, as well as sound. And then it transmits it to our web interface, which then, using a set of algorithms, determines useful information for the user. So for example, is my refrigerator door open or closed? Is my stove on or off? Things like that. So it basically converts data into a statement that's actually useful and understandable by a user. And so along the process, we've been trying to optimize for two things. One is cost, and the other is battery life. In terms of cost, we've used the most simple sensors available in terms of the four that I mentioned. To be more specific, each of them are less than $2 in unit cost, and they're the cheapest that you can go. And then in terms of battery life, we've created a system where we're dynamically modifying code, dynamically modifying the measurement frequency as well as the posting frequency of the device so that you can extend the battery life for as long as possible just through clever coding. And so at this point, I'll walk through our system model or our system design. Basically, there are three layers. There's your user layer, an API layer, as well as a database layer. The user layer comprises of two things. One is our device itself, and the second is a web interface from which the user can just indicate what exactly the device is being placed on. So for example, is it being placed on a stove? Is it being placed on a refrigerator? We've made modifications through each so that we can best detect the state of the actual appliance. So let's take the use case of a refrigerator. So essentially what you do is you place your device inside of the refrigerator. It will collect sensor data based on what it feels is useful. So for a refrigerator, sound is not really useful, vibration is not really useful, but light is, because when you open the door, the light tends to turn on in most refrigerator models. And temperature is, of course, useful because if the refrigerator starts getting warm, you have a problem. And so we only take a look at those two the data from those sensors initially, and those get sent over to our API, which then stores them into our database. The database processes these, and then tries to figure out what's going on. So has something interesting happened? So specifically in terms of device state, has the refrigerator gone from open to closed? We're trying to determine that. And so if it's been closed for a long time, but then suddenly we detect that something has changed, the light is on and it's open, we want to update the device sensitivity to make sure that we're actually validating what's going on. So for instance, we'll have the measurement frequency increase and we'll have the posting frequency increase so that we on the back end can determine with relative confidence that, okay, there's actually been a state change, and then we can notify our user as such. So we're not just passing along useless information that hasn't been verified. And so what's interesting is that our feedback loop updates the measurement frequency and the device frequency directly into the code so that our device can remain as dynamic as we want it to be and can fit the use case for whatever appliance the user chooses to use. And so with that said, I'll pass it along to Geoff, who will go over our exact implementation.
All right, so the interesting thing for us is determining the device state, as we said. The way we go about doing this is a vector comparison. We look at the vector of sensor data coming in, and we compare it to the known states we have in our database. In order to improve this, we also weight the different sensors according to their value to an appliance. So certain appliances obviously utilize different sensors more than others. So our example here, we have a dryer where we've given a 30% weighting to the value of sound, a 60% weighting to the value of vibration, a 10% weighting to the value of light, or to temperature, sorry. Now, light is not really used in a washer or dryer, so thus we have not utilized that in our calculation. Sound and vibration are much more important than temperature in determining the state of a washer or dryer. So thus, those have been weighted higher. So the way that we do this is we look at the weighted comparison and we select the state at which the value is closest to. So this is similar to a distance calculation in linear algebra. So here we have the device itself. The device is made up of a Arduino Uno, a Arduino Wi-Fi shield, and then a set of 4 sensors, including the electret microphone, the piezo vibration sensor, the light photocell, and we have a temperature sensor as well. We're actually going to show you a demo of how it works as well. I was hoping to open up everything to you guys, but since my computer decided not to work with VGA, I will show you as much as possible. So to start, we're going to enter a phone number so that it can be notified. And then, so this has been added to the database. So, Sonny, you want to? So what we're going to be doing here is replicating something similar to a fridge, where we will be utilizing the temperature and light sensors. So Sonny's going to be squeezing the temperature sensor while covering the light sensor. Let's see. All right, so here we can see the data coming in. Good timing, I'm awake. So if we go to device data here, and we refresh this, we should see it has gone up from 665 to 666. And we'll refresh it again. All right. Confirm it is coming in. All right. So now we have 3 on states. So usually this would send a text message. Unfortunately, due to the service in this room, we are not receiving the text. But you can see we've detected 3 on states in a row. So the reason we use 3 on states or 3 consistent states in a row is because we have the advantage of working with appliances that have consistent states. So we don't want to be kind of at the whim of someone bumping an appliance or adjusting an appliance for just a second. We want to make sure that we're seeing consistent states before we detect them. So we have 2 things. We have single state detection, which would be one of these lines, and then we have appliance state detection, which looks for 3 consistent states. So you've seen 3 off states and 3 on states, so therefore we can say it goes from off to on, and normally we notify you with a text message. So in general, we had a lot of success with this. The refrigerator worked perfectly every time. It's kind of very straightforward because you're using light and temperature, and it's extremely consistent. With the washer and dryer, we ran 10 tests. The first 5 of which were just generic tests, and all of those passed. And then with each sequential test, we added more noise to it, so adding sound vibration to the actual device to try to trigger it. And so on the last test, we were able to trigger it enough where it did detect it, but I guess that's one of the issues with using simple sensors, because they are binary in how they act. Here's a cost breakdown of our device. So part of the things we were optimizing for was low cost, because obviously if we're trying to tell you you should smarten your appliances and we're charging you a couple $100 for it, you might consider just buying a new appliance. So to break it down, as we bought it, it was about $116. But this was utilizing the Arduino Wi-Fi shield, which is, for our sake, simplicity, but at the same time it is generally considered way more costly than it would need to be. So using an alternative shield and doing this in bulk, in other words, over 100 units, we could easily get it down below $60. And this is with no customization. This is simply using parts that we can buy off SparkFun. So we were pretty pleased with the ability to do that. Comparatively, I don't know if you guys know Twine. Twine costs about $150. There's a similar device called Spotter that costs about $55 to $60 as well. So this is in a good price range for something that someone could buy and enhance their appliances. So in total, we were able to achieve state detection of a household appliance using these simple sensors and keeping it at low cost. We were able to implement a feedback loop, which allowed us to update our code remotely and thus limit the amount of posts we're doing. So we're not consistently posting. Each time we post, the device receives data back saying change measurement frequency to blank and post frequency to blank. It then integrates those into the code and integrates that into its waiting loop. And then this allows us to conserve power throughout the usage of the device. Finally, we're able to implement an interface as well as notifications. So we have a web interface that allows you to enter the device ID as well as the appliance that it's on. And then we also have the notify for your phone. Along with this, we actually integrated with this, a Belkin smart switch. This allows us to flicker the lights based on what you want or what states happen. So for example, at home, we have this set up to flicker my lights once the dryer has completed. And so this is kind of one of the, originally at Future Work, we wanted to implement it with actuators. But we were able to get this working, and it kind of was a demonstration of the fact that given more actuators, we'd be able to add more functionality given our device data specifications. And other future works would obviously be to consumerize the design, because as of now, none of us are EE or ME, and so we don't have particularly strong circuitry and design backgrounds. And so it's a very simple device in terms of visual right now, but obviously as you go forward, you'd want it to be something that could be appealing and simple and small in someone's household. And that's SmartSkins. I'd like to open up the floor for questions. Yes, sir.
I guess I'm wondering at the applicability of this. I mean, new appliances, for example, washers and dryers, produce significantly audible sounds when they're turned on and when they turn off.
Yes.
I mean, it just sounds like to outfit a number of your appliances with this sensor, you would be spending a lot of money when new appliance designs already have a capability for telling you when they're on and off.
So the idea isn't simply for notification purposes. So for example, one of the additional things that you can do with this is build layers. So for example, if your washer is just finished and your dryer is not finished, you don't get notified. But if your washer is finished and your dryer has finished, then you get notified, thus something valuable has happened. Or something like your fridge where you've stepped away, it maybe makes a slight beep, but you've stepped away from the room, and it can notify you that your fridge has been left open for an extended period of time, which is something that even with a small notification may not be valuable. But with a text message, so if you're out of the room, you can receive it, is valuable. Along with this, it's the action based on this, so it's the ability to actually act upon these states. So we've set it up so that we can use something like the Belkin Smart Switch, which would allow us to theoretically turn off an appliance if it was plugged in through the switch. So things like that, where it's actually the actuation and the, not simply a sound notification, but a notification that tells you something valuable beyond the sound. Anything else? Yes?
Have you considered tying a diagnostic test if it's not working and what's wrong with it?
Yeah, so a couple things that we would like to add is something like that where we have a way for the user to interact with what's going on the device so they can understand what's going wrong if it's misdetecting something. As well as that, right now we have the Wi-Fi stuff enabled through an Arduino sketch, and so we would need to build kind of a user interactive setup that would allow us to have them enter a Wi-Fi thing and update the sketch directly. Because unfortunately we can't do the remote update of the sketch if we don't have Wi-Fi hooked up. So kind of things dealing with the physical device in terms of consumerization are still kind of open to places we'd like to continue. Anything else? Thank you very much.